Interferometry is one of the most interesting tools in optics research. A measurement involves splitting and recombining light to analyze the difference in distance traveled by one light beam compared to the other, using the intensity of the resulting light to measure distances smaller than a human hair. The experiment is based on constructive and destructive interference. When the positive peaks line up with themselves, they increase in amplitude, constructive interference, and when the negative and positive peaks line up, they cancel each other out, destructive interference. Here is a schematic of the Michelson interferometer setup. We have a laser, mirror 1 and 2, a beam splitter, and a final viewing screen where the two light waves are added back together. This light is split and follows two paths noted by the red and orange on the picture. The interference pattern is then viewed on a screen or a wall. As one beam changes in length, the light wave phases oscillate, causing radial movement of the stripes or fringes. 3 separate interferometry experiments were conducted in the lab: measuring wavelength, lambda, measuring refractive index of air, and measuring refractive index of glass. In the first experiment, measuring the wavelength, the path length is changed by altering the position of the movable mirror using the micrometer knob. The fringes were counted and the mirror's movement measured with a precision of 0.1 millimeters. These figures are then put in our equation. Lambda, or wavelength, equals 2 times the distance to the mirror divided by the number of fringes counted. The result of 640 nanometers plus or minus 10 nanometers was found using statistical weights and agrees with the laser's stated wavelength of 632.992 nanometers. The second experiment uses a glass vacuum chamber. We don't move the mirror in this experiment. The optical path length is actually dependent on the refractive index, and the flickering fringes are counted as the chamber has the air gently pumped out of it. Lambda, the wavelength of the laser, equals lambda naught, the wavelength of the light in a vacuum, divided by the refractive index of air in this instance. With absolute pressure on the x-axis and big N, the amount of fringes, on the y-axis, we can create a graph where the slope is proportional to the slope of a graph with the pressure versus refractive index. The accepted value of 1.0000293 for the refractive index of air falls outside of our results and uncertainty, but agrees within 0.0006%. The third experiment measures the refractive index of glass. By slowly rotating a piece of glass, the length the light beam travels through it can be changed, and once again the fringes can be counted. Using this equation, where T is the thickness of the glass, theta the angle the glass is rotated, N the number of fringes, and lambda the wavelength of the laser in a vacuum, the refractive index of glass can be calculated. The results agree with the accepted value within 6%, however fall outside of our uncertainty. The sample size for this experiment was relatively small, and accuracy could be improved with more data points.